Okay, so this lecture I've organized into 4 parts. And the first I thought would be a brief review of kind of basic concepts associated with quantum entanglement, ultimately lead into the standard definition of entanglement entropy, right? Because again, the context is that the RT formula in ADS-CFT states a relation between the entanglement entropy on the boundary with certain constructions in the bulk. Right? So to fully appreciate it, in the first part, I'm going to do this brief review of the definitions of quantum entanglement and ultimately entanglement entropy. And then in part 2, I'd like to look at 3, let's call them 3 predecessors of the RT formula that are formally similar to the RT formula. And we'll look at some of the motivations for these other formula. So the 3 are the famous Beckenstein-Hawkins formula for black hole entropy, a formula for entanglement entropy in quantum field theory. And then the last example is a slight extension of entanglement entropy for quantum field theory that leads to this concept of topological entanglement entropy. And then in the third part of the lecture, we'll finally get to the RT formula. And here I'd like to discuss one interpretation of it given by von Ramstonk fairly recently that I'll call the connectedness entanglement hypothesis. And it's this interpretation that suggests that the RT formula states a duality between entanglement on the boundary with certain, as we'll see, spatio-temporal constructions in the bulk. And I'd like to consider the extent to which we can consider it to be a duality in part 3. And then in the last part of the lecture, I'll step back and consider the question of what would it take to establish a duality. And as I understand it, a duality is a one-to-one relation between space-time topology on the one hand and quantum entanglement on the other. And I'll address this question from the point of view of 2 approaches, a state-based approach and an observable-based approach. Let me begin with this review of hopefully concepts that we're all familiar with. One goal of the review is to maybe establish the terminology for later parts of the lecture. Right. So ultimately, this review is going to remind us of the definition, one common standard definition of quantum entanglement, and the definition of entanglement entropy. So towards that end, let's briefly remind ourselves of a bunch of definitions lead into it, right? So the first is the definition of a density operator in quantum mechanics. So a density operator rho for a system in one of a number of vector states, each with some assigned probability p sub I, is defined to be a weighted sum of projection operators onto the individual vector states weighted by the corresponding probability. Where, of course, the sum of the probabilities has to be 1. By this definition, right, a density operator can correspond to more than one ensemble of vector states, whereby an ensemble of vector states, I mean just a collection of vector states with a probability distribution assigned to them. So here are 2 distinct ensembles of vector states, each contained in 2 vector states with corresponding probabilities. Right? So they're different ensembles, but we can represent them using the same density operator, provided the vector states are related in an appropriate way. Why use density operators to represent states as opposed to vectors? Right? And we're commonly told that if we use a density operator, then we can make this distinction between a pure state and a mixed state, where a pure state is a density operator that can be expressed as a single projection operator onto a a single vector state. If a density operator cannot be expressed in this way, then it's called a mixed state. Now let's remind ourselves of the standard warning against ignorance interpretation and ignorance interpretation of mixed states. So here's a generic mixed state. Rho equals, right, some probability times the projection operator onto vector state psi1 plus another probability times the projection operator into psi2, etc. And on the surface, if the state of our physical system is represented by rho, this might suggest that we don't know what vector state our system is in, right? It could be in vector state psi1 with probability p1 or psi2 with probability p2, etc. Right? So this suggests an ignorance interpretation of a mixed density operator state. But again, the standard warning is, well, there are two concerns with this ignorance interpretation. And the first is, right, from the previous slide, a given density operator can represent more than one ensemble of vector states. And a second concern is that an ignorance interpretation cannot be applied to a mixed state of a subsystem of a composite system when that composite system is in a pure entangled state. And we'll see this by a standard example in a couple minutes. Right, so when you read in the literature about density operators represent an uncertainty as with respect to states, you should take that with a grain of salt. And there's a quick and dirty test, right, to determine whether or not a density operator is pure or mixed. If the trace of its square is equal to 1, you can demonstrate that that entails it's pure, and if the trace of the square of its the trace of the square of the density operator is less than 1, then the density operator is mixed. Or the trace of an operator is the sum of the diagonal elements of a matrix representation of it, and with respect to some basis. Now, entanglement involves multipartite states, right? In other words, vector states that are elements of a multipartite Hilbert space, a Hilbert space that can be decomposed into a product, right? An n-partite product space. And there, with respect to such an n-partite product space, there are 3 different types of density operator. So a product density operator is a density operator that can be written as the product of n terms, where each term is a density operator on the corresponding factor space. A separable density operator on a multipartite product space is a density operator that can be written as a sum of product density operators, a weighted sum of product density operators, right, where the sum of the weights equals 1, and each term in the product, again, is a density operator on a corresponding factor space. And then finally, a non-separable density operator is a density operator that is not separable. So in addition to multipartite states, entanglement also involves correlations. So towards defining the notion of a correlation between observables with respect to a density operator state, let's recall the definition of the expectation value of an observable with respect to a density operator state, right? And that's defined to be the trace of the product of the density operator with the operator that represents the observable. Recall the intuition underlying this definition is the following, right? The expectation value is supposed to be the average value of the observable with respect to the state rho. And since density operators represent ensembles of vector states, the average value of O with respect to the density operator state rho should be a weighted sum of the value of O in each vector state, weighted by the corresponding probability. Right? So the expectation value of O with respect to the density operator rho should be the weighted sum of its expectation values with respect to the vector states in the ensemble that the density operator represents, weighted by the corresponding probabilities. And it turns out, right, this definition in terms of the trace, if you expand out the definition of the trace, you get the expression that underwrites this intuition. Correlated observables, right? So let OA and OB be operators on Hilbert spaces HA and HB with identity operators IA and IB respectively. Then the observables represented by OA and OB are correlated with respect to the density operator state rho just when the expectation value of the product operator OA cross OB with respect to the state rho does not factorize into the expectation values of the individual operators OA and OB separately. And the intuition for this definition can be drawn from the corresponding situation involving vector states. So you can show the Born rule entails that this corresponding non-factorizability condition for expectation values with respect to vector states holds if and only if the corresponding Born probabilities satisfy this inequality. Right? Where on the left is the joint probability of obtaining values little a and little b of the two observables, and on the right are the marginals, right, of obtaining the values for OA and OB separately. Right? So when the joint probability is not equal to the product of the marginals, we say that the observables are statistically dependent with respect to the vector state psi. The intuition then is statistical dependence is an indication of a correlation. The definition of correlated observables with respect to a density operator state. Now, you can then demonstrate the following claim. Observables represented by the operators that appear in a product operator are uncorrelated in a product density operator state and correlated in both separable and non-separable density operator states. The intuition underlying this claim can be motivated by the simple bipartite case. Right? So the claim is the bipartite operator OA cross OB, the expectation value of it with respect to a product density operator state factorizes, right, by definition of the trace, whereas the expectation value of this product operator with respect to a separable state does not factorize, and neither does the expectation value of the product operators with respect to a non-separable density operator state. Right. So in the latter two cases, that's an indication of correlations. And at this point, authors argue that the correlations associated with product operators with respect to a separable density operator state can be classically explained. They can be generated by classical operations, insofar as they're the result of a classical mixture of product states, whereas the correlations associated with observables in a non-separable density operator state cannot be so explained. The term is that those correlations are non-classical. They cannot be explained in terms of a classical mixture of product states by definition of a non-separable density operator state. So this distinction between classical correlations in a separable state versus non-classical correlations in a non-separable state then motivates the standard definition of an entangled state. A state represented by a multipartite density operator rho is quantum entangled just when rho is non-separable. And here are two examples, maybe to make this definition a bit more concrete. Right? In the first example, we have a mixed separable density operator state that potentially exhibits classical correlations. And in the second example, we have a pure non-separable and hence entangled density operator state that potentially exhibits non-classical correlations. So having presented this standard definition of an entangled state in quantum mechanics, at this point, we should be aware of the following qualifications, right? As presented in an article within the past decade by John Ehrman on some puzzles and unresolved issues about quantum entanglement. So Ehrman pops up in the form of this robot from the 1960s television series Lost in Space. The robot goes around exclaiming, "Warren and Will Robinson, danger." And the danger here, according to Ehrman, is that there are at least 4 distinct definitions of a quantum entangled state, right? One of them being the previous definition in terms of non-separability. And Ehrman, in this article, Ehrman provides counterexamples to each of these 4 definitions. Right? And then he goes on, moreover, to warn us that, quote, the implicit assumption in most of the philosophical literature and a good deal of the physics literature on quantum computing and quantum information theory that the composite system algebra has the structure of a tensor product of type 1 factors is to be deplored because it neglects possibilities that need to be explored. So here he's concerned about the notion of entanglement, for instance, in quantum field theory, which, because of the nature of infinite degrees of freedom associated with such theories, it turns out the state spaces have the structure of what are called non-type 1 factors. And this really, intuitively, this entails that we cannot decompose the Hilbert space of a typical quantum field theory into a nice product of factor spaces. And that problematizes the definition of entanglement. At least it problematizes, right, any definition that assumes your Hilbert space has this nice decomposition into product spaces, into factor spaces. But having been made aware of this concern and this article by Ehrman, for our purposes, for the purposes of this lecture, for the purposes of introducing and understanding conceptually, right, the implications of the RT formula, we will stick with pure bipartite states for the most part. The really simple examples for which entanglement perhaps can be unproblematically defined. And we'll deal with these problematic non-type 1 factor algebras that Ehrman is concerned about in 1 or 2 occasions when they arise. All right, so the point here is that we should be aware that the definition of quantum entangled state is not without its controversy. All right, so let's return to our exposition. So now that we have at least the standard definition of quantum entangled state, let's finish up the review by reminding ourselves of the definition of one proposed measure of entanglement as represented by the concept of entanglement entropy. And to get to entanglement entropy, let's slog through a few more definitions. So let's remind ourselves of the definition of a reduced density operator. So let's let rho sub A be a density operator for a composite system that decomposes into 2 subsystems A and B. Then the reduced density operator for one of the subsystems, say A, is defined to be the partial trace with respect to the degrees of freedom of the other subsystem, in this case B, of the density operator for the composite system. Where the partial trace of a bipartite operator is defined to is given by tracing out the degrees of freedom of one of the subsystems. So as an example, right here is a non-product vector state, psi AB. It's a 2-qubit state. The corresponding density operator, rho sub AB, is given by this expression, right? This is a pure non-separable and hence entangled state. We can then derive the reduced density operators for both of the subsystems, and they're given by these expressions. Ultimately, they're proportional to the identity operators. And both of them are mixed density operator states. And it's this example that underwrites one of the two concerns about ignorance interpretations of mixed states. Right? So the two reduced density operators are mixed states. If we apply an ignorance interpretation to them, that would suggest that the two subsystems, the two qubits, A and B, are in unknown vector states. Right? Rho sub A suggests under an ignorance interpretation that qubit A is either in the state 0 with probability of a half or the state 1 with probability of a half. And similarly, rho sub B suggests qubit B is in the state 0 with probability of a half or the state 1 with probability of a half. We just don't know which of these two vector states the two qubits are in. But this would suggest that the density operator for the combined 2-qubit state should look like this. Right? This is the density operator in which qubit 1 seems to be in state 0 with probability of a half, and qubit A, and qubit B is in state 0 with probability of a half, and similarly, qubit A is in state 1 with probability of a half, and qubit B is in state 1 with probability of a half. But by assumption, that is not the density operator for the composite state system. Right? That density operator is given by this expression up here. All right, so the definition for a reduced density operator. With that in hand, we can then remind ourselves of the definition of Entanglement entropy of a density operator state. And this is defined to be minus the trace of the product of the density operator with its log, rho log rho. Now, you can then show that the Entanglement entropy of a density operator varies from 0 for a pure state to log n for a maximally mixed state, given which is proportional to the appropriate identity operator. And this claim then indicates that explicitly, right, the von Neumann entropy is a measure of mixedness. It's a measure of the degree to which a given density operator is mixed. Now, it turns out there are other proposed ways of interpreting the von Neumann entropy, right, of a density operator. And I think we should all be aware of these different alternative interpretations. I'm going to consider 3 of them in the form of asides, right? They're not really relevant to the topic of this lecture, but again, I think we should be aware of them. So the first aside is the option of interpreting the von Neumann entropy of a density operator as a measure of information compression, right? And I take it this interpretation is motivated by the analogy between the von Neumann entropy on the one hand and the Shannon entropy and classical information theory on the other hand. So the Shannon entropy is defined with respect to what we might think of as an ensemble of classical states, right? A collection of classical states, little x1 through xn, with a probability distribution defined on them. And the Shannon entropy of such an ensemble of classical states is defined as, right, the weighted sum minus the weighted sum of log 2 of the probabilities weighted by those same probabilities. And then there's an argument in classical information theory that underwrites the claim that the Shannon entropy so defined specifies the minimal number of bits required to encode the output of a classical information source, right? One of the states of a classical ensemble, an ensemble of classical states. It turns out the von Neumann entropy can be rewritten in a form that's formally identical to the Shannon entropy. And the only difference is, right, the von Neumann in the von Neumann entropy context, the ensemble of states is an ensemble of quantum states, vector states, whereas Shannon entropy refers to an ensemble of classical states. But right, the analogy is then motivates this interpretation that the von Neumann entropy of a density operator state specifies the minimal number of qubits required to encode the output of a quantum information source, right? A source that produces quantum vector states from an ensemble. So that's aside one. Another alternative interpretation of the von Neumann entropy is based on another way of interpreting the Shannon entropy, right? So aside two, the Shannon entropy can also be interpreted as a measure of uncertainty. In this context, we're told to identify this expression, minus log to the base 2 p sub I, as the information gained upon finding our system to be in one of the states of an ensemble of classical states, namely the one corresponding to the probability p sub I. And the intuition here is that the lower the probability of a state, the more information gained when we measure the system and find it to be in that state. Whereas the greater the probability of a given state, the less information we gain when we measure the system and find that it's in that state. So then the Shannon entropy is then interpreted as the expectation value of the information gained when we measure our system and find that it's in one of an ensemble of classical states. And by analogy, right, this motivates the interpretation of von Neumann entropy as the expected value of information gained upon measuring our ensemble of vector states with a particular outcome. But this interpretation of von Neumann entropy, again, should be swallowed with a bit of salt, again, because explicitly, right, the von Neumann entropy is a measure of the degree to which the density operator state is mixed. And as we saw, mixedness does not necessarily entail uncertainty. All right, and as the last aside, there's also an interpretation of the von Neumann entropy as simply thermodynamic entropy, call it S sub T. And whether or not you subscribe to this interpretation seems to depend on your answer to the following two questions. First, is a quantum measurement associated with an increase in thermodynamic entropy? And second, is a quantum measurement associated with a transition between a pure state and a mixed state? And I take it von Neumann originally answered yes to both of these questions. And this was the motivation for him to initially introduce what we now call von Neumann entropy. But at this point, let me leave this aside with the following observation that this is still a fairly active debate in philosophy of physics, and also in physics too, right? There are some philosophers who think there are flaws in von Neumann's original argument, and other philosophers have suggested no, these flaws can be addressed, right? And this is still an ongoing debate. This recent article by Prunkel from 2020 is a good introduction to this debate. But for the purposes of this lecture, I think I'll leave it at this point. So that's von Neumann entropy, and what it measures explicitly, mixedness, and 3 potential alternative interpretations of it. So now we finally get to the definition of entanglement entropy, right? One proposal for a measure of entanglement. So the definition is the following: for a bipartite system AB with density operator rho sub AB, the entanglement entropy S sub A of one of the subsystems, say subsystem A, is defined to be the von Neumann entropy of the reduced density operator associated with that subsystem. And by definition of von Neumann entropy, that's equal to minus the trace of the reduced density operator times log of the reduced density operator. Now, again, just as von Neumann entropy explicitly is a measure of mixedness, so is entanglement entropy. S sub A is a measure, in the first instance, it's a measure of the degree to which the density operator rho sub A is mixed. Now, you can demonstrate the following claim. If rho sub AB, the density operator that represents the state of our composite bipartite system, is a pure state, then it is separable if and only if the entanglement entropy with respect to A is less than or equal to the von Neumann entropy of the composite pure state. And this indicates the following: if a bipartite system is in a pure state, and if entanglement is defined in terms of non-separability, then the entanglement entropy of one of the subsystems of the bipartite system is a measure of the degree to which the density operator of the composite system is entangled. Or more provocatively, in this context, the entanglement entropy of subsystem A can be thought of as a measure of the degree to which subsystem A is entangled with subsystem B. So I take it that's the sense in which entanglement entropy is a measure of entanglement. Now, having said that, right, again, let's just remind ourselves once more of Ehrman's-Wernin in the general case of mixed states for systems that can be decomposed into more than 2 parts. This simple way of measuring entanglement of entanglement might break down, right? In this more general case, in fact, there's a large literature on different proposals for measures of entanglement for the general case of mixed states and in partite systems for n greater than 2. Again, for the purposes of this lecture, I'm going to sweep all this literature under the rug and represent it by that portion of our conceptual map associated with dragons. So at this point, I'd like to conclude this review of the standard definition of quantum entanglement and this one proposal of a measure for it as embodied by entanglement entropy. Again, right, the context is going to be the RT formula is a formula that relates entanglement entropy on the one hand to on the boundary to various bulk constructions. So I'd now like to move on to part 2. And this part involves a review of 3 formula that formally are similar to the RT formula. The Beckenstein-Hawkins black hole entropy formula, the formula for what's called geometric entanglement entropy in the context of quantum field theory, and then finally a slight extension of the latter to what's called topological entanglement entropy. So the first of our 3 ancestors is this formula, the Beckenstein-Hawkins formula for black hole entropy, introduced in an article by Beckenstein in '73. So the quantity on the left is the entropy associated with a black hole, and on the right is the area of the event horizon of the black hole divided by 4 times the Newtonian gravitational constant. There are at least 2 ways to motivate this formula, one from thermodynamics and the other from statistical mechanics. And here I'm following a review article by David Wallace from 2018, where he describes these motivations. So in the thermodynamical category, it turns out small scale interactions between black holes and other states of matter can be characterized as reversible and irreversible, with the horizon area playing the role of thermodynamic entropy. This was argued in a paper by Christodoulou and Ruffini in '71. And then stationary black holes satisfy a formula that is formally similar to the first law of thermodynamics, provided, again, we identify the area of the event horizon with thermodynamic entropy, and the surface gravity of the event horizon with thermodynamic temperature, right? And the argument for this was given in this famous article by Bardeen, Carter, and Hawkins on the laws of black hole mechanics in '73. And then finally, there's Hawkins' area theorem in general relativity that states that in finite processes involving black holes, the change in area of the event horizon has to be greater than or equal to 0. And the analogy here is with the second law of thermodynamics. So in addition to these thermodynamic motivations for the Beckenstein-Hawkins formula, there are also statistical mechanical motivations, according to Wallace. So the intuition here is the following. If black holes are thermodynamical systems, then just as with other thermodynamical systems, black holes should have a statistical mechanical description too, right? We should be able to assign to them, for instance, a Boltzmann entropy, a statistical mechanical entropy, given in terms of the number of possible microstates they can be in. And if we use the Beckenstein-Hawkins black hole formula for black hole entropy in this expression, then we get an expression for the number of possible microstates of a black hole as a function of the area of its event horizon. And evidence for this formula comes from calculations in effective field theory, string theory, and indeed ADS-CFT. So that's the Beckenstein-Hawkins black hole entropy formula, right? So it relates a concept of entropy on the left, either thermodynamic entropy or statistical mechanical entropy, with a spatiotemporal construction on the right, namely area of event horizon of a black hole. The second ancestor of the RT formula is this expression. This is referred to by some authors as geometric entanglement entropy. And it's the entanglement entropy for a quantum field theory defined on a background spacetime, right? So the idea is we identify 2 regions of the spacetime, a region R and its complement separated by the boundary of R. And then we decompose our quantum field into degrees of freedom localized in R and degrees of freedom localized in its complement, and then calculate the entanglement entropy of the degrees of freedom localized in R. And it turns out we get an expression that's proportional to the area of the boundary of the region R, del R. And this formula was derived by Sretnicki in a 1993 article in which he calculates the entanglement entropy of the ground state of a free massless scalar quantum field with respect to a spherical region R of spacetime. And he shows that it's proportional to the area of the boundary of R. And to motivate this area formula, he makes the following statement, which I interpret as a thermodynamical motivation. Right? So he says, entropy is usually an extensive quantity. So I assume he's referring to a thermodynamic entropy in this context. So we might expect the entanglement entropy at S sub r to be proportional to the radius, to the volume of the region R. But he then goes on to say, well, SR, in this case, SR equals SR bar. And he takes this to mean that SR should depend only on properties which are shared by the two regions. And the one feature they have in common is their shared boundary. So assumedly, by assuming SR equals SR bar, I think that's equivalent to the assumption that the state of the quantum field is a pure state, of the vacuum state is a pure state. Now, in another article around this time, Kalin and Wilczek derive essentially the same formula, and their derivation, what they derived this the entanglement entropy of the ground state of a free scalar field with respect to a conical region of Euclidean spacetime, and they show that it's identical to the statistical mechanical entropy of a Euclidean black hole. And there's this method of calculating the entanglement entropy of a quantum field that they introduce in this article that's come to be called the replica trick. And I take it they're motivated here by statistical mechanical motivations, insofar as the form of the formula for the entropy of the black hole that they derive assumes that it's statistical mechanical in nature. So they claim that the statistical mechanical black hole entropy and the geometric entanglement entropy are the classical and first quantum contributions to a unified object measuring the response of the Euclidean path integral to the introduction of a conical singularity in the underlying geometry. Now, one feature of entanglement entropy in the quantum field theory context is this UV divergent nature. So most authors argue that entanglement entropy in quantum field theory is divergent in the UV limit. And this is demonstrated argued for by in a number of different ways. So there are authors who show this divergent nature by means of explicit calculations, and this goes back to this influential article by Ed Hooft in 1985, where he, among other things, he shows that the free energy for a scalar field in a background black hole spacetime diverges as the event horizon is approached. And if the free energy diverges, so does other quantities derived from the free energy, like the entropy. And in Srednicki's derivation, he only gets this result by inserting a cutoff into his field theory. So the form he derives involves a cutoff. And in the derivation of Kalin and Wilczek, there's a divergence associated with the conical singularity. Now, other ways of demonstrating this UV divergent nature include lattice theoretic estimates. So in his series of lectures on entanglement entropy, Heydrich derives this estimate of the entanglement entropy of a quantum field theory in a lattice, which is inversely proportional to the lattice spacing, right? And so as the lattice spacing goes to 0, you get this divergence. Now, yet other authors appeal explicitly to the infinite degrees of freedom of a quantum field theory. So von Ramstonk, in his lectures on gravity and entanglement, states that the subsystem we were talking about actually contains an infinite number of degrees of freedom. Since we have field modes with arbitrary short wavelengths, then sum in the contribution to the entanglement entropy with respect to this region R. From these infinite numbers of modes, we obtain a divergence proportional to the area of the boundary. And Hartman, in his lectures on quantum gravity and black holes, makes a similar statement. In a continuum quantum field theory, there are UV modes at arbitrarily small scales across the dividing surface. And this makes it impossible to actually split the full Hilbert space. So here he's referring to the infinite number of degrees of freedom of a quantum field theory as an obstacle to a simplistic bipartition of its Hilbert space into two factor spaces. And this latter statement of Hartman's, I take it, can be made rigorous in more rigorous formulations of quantum field theory. So this is the last way of perhaps demonstrating the UV divergent nature of quantum field theoretic entanglement entropy. So here we're appealing explicitly to this non-type 1 nature of the algebra of observables that appear in quantum field theories. Right? This is the warning that Ehrman gave us a while back. So in an article 2020, Noel Swanson demonstrates this following what he calls a no-go lemma in the context of the algebraic approach to quantum field theory. Right? So any model of the Haag-Kessler axioms with a well-defined UV scaling limit, if the local double cone algebras are not of the simple type 1, then there's no pair of Hilbert spaces and an isomorphism from our state space of our theory to the product of these two Hilbert spaces, such that we can essentially represent the algebra, the operators associated with any double cone region and the complement of the double cone region in terms of operators only confined to one of these two Hilbert spaces. So here's a rigorous way of stating this claim that in quantum field theory, you can't naively split the Hilbert space into factor spaces. And Swanson goes on to point out that this obstacle is not a consequence of the Riesz-Schlieder theorem, which is another result in algebraic quantum field theory that indicates, in particular, the vacuum of a typical quantum field theory is generically is entangled across any generic space-like separated regions. But this UV divergent nature is not a consequence of the Riesz-Schlieder theorem, right? Or a consequence of this non-type 1 nature of the algebra observables in QFT. All right, so that's the concept of geometric entanglement entropy. So now we have a formula that relates entanglement entropy on the left to a geometric construction on the right. And the last ancestor of the RT formula I'd like to review is this extension of geometric entanglement entropy to what's called topological entanglement entropy, which includes a second term on the right. Right? And this second topological term was introduced independently in two articles in 2006 by Levine and Nguyen and Kataev and Preskal. So their intuition is the following, right? The formula for geometric entanglement entropy encodes kind of a geometric aspect of entanglement entropy, assumingly in the form of local short-range correlations. And Levine and Nguyen and Kataev and Preskal suggest we also need, in addition, a term representing a topological aspect of entanglement entropy, a topological contribution to entanglement entropy. that encodes perhaps non-local global long-range correlations. And this is the intuition of Levine and Wynn, right? They suggest that a non-zero value of this gamma term, quote, signals the presence of non-local correlations. And what they go on to characterize as topological order. So the motivation for this claim, for this intuition, is the following example due to Levine and Wynn. So they ask us to consider 4 regions of space, and a similar argument is given in Katave and Preskel's article, but they use a different configuration of regions. So in Levine and Wynn's example, we have these 4 different regions of space. These are the red regions, A, B, C, and D, with B being identical to A except for the fact that B is missing the top bar that A has, and similarly C is identical to A except for a missing bottom bar, and D consists of 2 disjoint regions. It's just missing the top and bottom bars of A. Right? And each of these regions, A, B, C, and D, divide the space into a red region and its complement separated by a boundary. Right? In the A region case, A has 2 boundaries, del A1 and del A2. Similarly, in the D region, in the D example, and in the B and C examples, there's just a single boundary. Right? And Levine and Wynn now suggest, now ask us to focus on this particular combination of entanglement entropies associated with these 4 regions. In particular, they ask us to calculate the difference between the differences of SA minus SB and SC minus SD. Right? SA is the entanglement entropy of a subsystem localized in region A with respect to a subsystem localized in its complement. And similarly for SB, SC, and SD. And they observe that, well, if we use the formula for geometric entanglement entropy without the second topological term and calculate this difference, we get 0. Right? So let's see, the idea is as follows. The entanglement entropy S sub A is given by the sum of the areas of the bounded surfaces, right? The sum of the area of area of del A1 plus the area del A2, right? In the 2-dimensional case, it's just the length of the perimeters of del A1 and del A2. Similarly, the entanglement entropy S sub B is the length of the perimeter del B. And the difference in these lengths, length of del A1 plus length of del A2 minus length of del B is equal to what the length of this section of del A2 plus the length of the section immediately above it. Right? That's what's missing in the B configuration. And similarly, the difference between SC and SD is given by the sum of this section of del C plus the sum of the section immediately above it. Right? That's what's missing in D with respect to C. And that's the same quantity as what we derived, what we calculated, what SA minus SB is equal to. Right? And so the difference between these 2 quantities vanishes. So the intuition here is, Levine and Wynn's intuition then is any non-zero difference in this quantity can only arise from a topological contribution to entanglement entropy, a contribution perhaps from an operator that can have support on A that cannot have support on C, for instance. Right? If such an operator contributes to the entanglement entropy of S sub A, it would not contribute to the entanglement entropy S sub C. And a non-zero value of gamma is supposed to indicate the presence of a correlation associated with such what we might call a non-local operator. So to make this maybe a bit more concrete, let's consider how we might make a distinction between local and non-local correlations. So here's the A region once again. And in this diagram, I've also represented 3 subregions, right? One is the non-contractible loop C that extends all the way around region A, right? Non-contractible in the sense that it cannot be continuously deformed into a point. And then there's a region Y contained in A that consists of a contractible region of points. And similarly, there's a region X in the complement of A that's also a contractible region, a contractible set, perhaps of lattice sites. And then we can identify operators that have support on these 3 regions, right? So an operator that only has support on the C region, we might think of as a non-local operator, right? Only in the sense that it only has, by definition, we might define it as only having support on C and be in the identity on, say, all lattice sites that aren't contained in C. A Wilson loop operator has those features. And operators with supports on contractible sets, Y and X, we might refer to as local operators. Local here only in the sense that, again, they have support on contractible regions of a given space. With that distinction, we then might make this distinction between a non-local correlation in terms of a correlation in which at least one of the observables, correlated observables, is a non-local operator. And a local correlation might be identified as a correlation in which all observables are local. And this seems to be the intuition of Levin and Wynn, right? So here's one way that their example has been characterized. So this is an account of Levin and Wynn's example by Patros in his text on topological quantum computation. So here he says the difference in Levin and Wynn's example, the difference SA minus SB has contributions that come from the upper horizontal part of the region A, right? Similarly, non-zero contributions to SC minus SD also come from the same upper part. If these entropies only had contributions from local correlations, if we only used the formula for geometric entanglement entropy to calculate them, then their difference would go to 0, right? As we discussed on the previous slide, when their respective regions become sufficiently large. The only possible contribution could arise from a non-local operator, like a Wilson loop operator, that wraps non-trivially around the region A. So again, the intuition is that a non-zero value of this second term in this formula for entanglement entropy indicates the presence of a non-local correlation contributing to the left-hand side. And that non-local correlation is due, according to Levin and Wynn's and Patros's intuition, is due to the presence of a non-local operator of the Wilson loop variety. Okay, so that's the concept of topological entanglement entropy, right? So again, to step back, it's another formula that relates entanglement entropy on the left-hand side to, in this case, geometrical and topological features of a space or space-time on the right. So that summarizes.
May I ask something a moment? The
Yes.
gamma that appeared here in the formula about topological entropy is connected with the Euler characteristic.
I'm sorry, is connected with
Euler characteristic.
No, I don't think so. No,
Okay.
I think it's just the same symbol.
Same symbol, there's no connection. Okay.
Yeah. Actually, the symbol I think that Levin and Wynn use is a lowercase gamma, but I thought I would use a capital
not connected
gamma.
with the number of the holes of the system. No, it's not connected.
Yeah, it's not associated with the Euler characters.
Okay. No, thank you very much.
Okay, so that's topological entanglement entropy. So with these examples in hand, let's now move on to part 3 of the lecture. Let's now consider the RT formula in its full-blown glory. And then I'd like to discuss one proposed interpretation of it, von Rahmstonk's, what I call von Rahmstonk's connectedness entanglement hypothesis. So here's the RT formula as originally presented in Ryu and Takayanagi's paper in 2006. Again, it relates, and so this is it's given in the context of ADS-CFT, right? And in that context, we need these particular constructions in order to state the RT formula. So we have a spatial slice through the bulk, intersecting the boundary in some boundary spatial surface. And we've decomposed that boundary spatial surface into a subregion R and its complement R bar. With respect to R, we define this bulk surface called the minimal area bulk surface associated with R. Right? It's the bulk surface that has the same boundary as R, and it's the minimal area such bulk surface. And in addition, there's this other bulk surface, the homology surface H sub R, that's defined as the surface whose boundary is the union of R, the bulk surface whose boundary is the union of R and gamma R. So the RT formula, as originally stated by Ryu and Takayanagi, is the statement that the entanglement entropy of a boundary subsystem localized on R is equal to the area of the corresponding minimal area bulk surface gamma R, divided by 4 times the Newtonian gravitational constant. So here again, we have another formula expressing a relationship between entanglement entropy on the left and some spatio-temporal construction on the right. But in this case, the formula is given in the context of ADS-CFT. Motivations for the formula. Well, recall that formally it's very similar to the 3 previous formula we've just discussed. It's the 3 ancestors. But here are some additional motivations. So one is an analogy with the Beckenstein-Hawkins black hole entropy formula. And I think this is given in the original article by Ryu and Takayanagi. So they suggest, well, in the particular case in which the bulk spacetime is ADS Schwarzschild spacetime, or asymptotically approaches ADS Schwarzschild spacetime, that's an example of a black hole spacetime. So we have a black hole in the bulk, in the limit in which our boundary spatial subregion R encompasses the entire boundary time slice, the corresponding minimal area bulk surface gamma sub R intuitively wraps around the event horizon of the bulk black hole and becomes the event horizon in this limit. And in fact, right, and that limit, when gamma sub r can be identified as the event horizon of a black hole, we get the Beckenstein-Hawkins formula, right? At least if we identify the entanglement entropy S sub r with either thermodynamic entropy or statistical mechanical entropy. So that's one sort of intuitive motivation for the RT formula. And then the RT formula itself then would just be a generalization to the case in which the bulk spacetime isn't necessarily a black hole spacetime. Alternatively, perhaps a more rigorous motivation comes in the form of an explicit derivation of the RT formula. And this was given in an article by Lukowitz and Maldacena in 2013, in which they derive an expression for the RT formula using Euclidean path integral techniques. And I think the method they use really imitates the method used originally by Kalin and Wilczek in their derivation of geometric entanglement entropy. So at least two motivations for the particular form of the original RT formula. Here are some qualifications for the formula, at least in its original form. So it holds in cases in which the bulk theory is a classical theory of gravity that satisfies the Einstein equations with a time reflection symmetry under which R is invariant. I take it the time reflection symmetry is required in order to be able to identify a boundary spatial, a time slice, right, with respect to which we can then identify R and then these corresponding constructions in the bulk. But that assumption can be relaxed. The time reflection symmetry assumption can be relaxed, and a covariant version of the RT formula can be formulated. And this was given in an article by Hubeny and colleagues. And moreover, an additional term on the right-hand side of the equation can be added, what's called a quantum correction term that roughly represents the degree, the entanglement entropy of a bulk system with respect to H sub r, degrees of freedom supported on H sub r. And this quantum correction was derived in this article by Faulkner and colleagues in 2013. All right, so that's the RT formula, right? And some motivations for it, and some slight extensions of it. How do we understand it, right? In the first instance, we might attempt to understand it as an additional entry in the ADS-CFT dictionary, right? It's relating a quantity on the bulk, a quantity on the boundary, the entanglement entropy associated with the boundary composite system with a bulk quantity, right? The area of a minimal area bulk surface corresponding to R. Now, von Ramstonk has suggested the following interpretation of the RT formula, at least in its original form. So call this the connectedness entanglement hypothesis. So here's the RT formula in its original form without the quantum correction term in particular, right? So von Ramstonk's intuition was, well, it's supposed to represent the entanglement entropy of a bipartite physical system on the boundary, right, with respect to some decomposition of degrees of freedom into those supported on some region R and those supported on its complement. So assumedly, the physical system on the boundary is in some entangled state with respect to this particular decomposition. So here's a generic entangled state, bipartite entangled state, entangled in the sense of a non-product state. in the context of a vector state as opposed to a density operator state. So here's an entangled state that might represent a state of a composite system on the boundary. With respect to this state, we can calculate the entanglement entropy of the subsystem localized on R, right? In terms of the RT formula. And as the entanglement entropy of R goes to 0, according to von Ramsdonk's intuition, we would expect this initial entangled boundary state to become disentangled. Ultimately, when SR is equal to 0, the state of the composite system on the boundary becomes a product state involving degrees of freedom localized in R and degrees of freedom localized in its boundary without any correlation between observables associated with these two states. And now if we apply the ADS-CFT correspondence, if we interpret the RT formula as a statement of one aspect of the ADS-CFT correspondence, right, the initial entangled boundary state is dual to some geometric configuration in the bulk, right, associated with a minimal area bulk surface, gamma sub R, that serves to divide the bulk spacetime, or at least this spatial slice of the bulk spacetime, into two separate regions, HR and HR bar. And in the limit as SR on the left goes to 0, the area of gamma sub R on the right should also go to 0. And if the area of gamma sub R on the right goes to 0, that effectively pinches off the bulk spatial slice into two disconnected regions, right? HR and HR bar. And von Ramsdonk's intuition is that this bulk configuration, spatial temporal configuration, spatial configuration corresponds on the boundary to this product state. And now von Ramsdonk asks us to consider the reverse process, right, in which we begin in the bulk with two disconnected regions and then increase the area of this minimal area surface separating them. And in this process, two disconnected regions become a connected region. And that process corresponds to the entanglement of two subsystems on the boundary. So according to von Ramsdonk, classical connectivity in the bulk arises by entangling the degrees of freedom of the two components of a CFT product state on the boundary. So does that make sense? So again, right, the idea is spatiotemporal connectivity in the bulk is dual to entanglement on the boundary. Now, one potential concern with this connectedness entanglement hypothesis involves the extension of the RT formula, right? So in its covariant version with the quantum correction term included, can we still maintain this connectedness entanglement hypothesis? Right, so it looks like, so here's the RT formula with the quantum correction term, right? The second term on the right. This seems to spoil the duality between entanglement on the boundary on the left and connectedness / topology in the bulk on the right, right? Now entanglement on the boundary is no longer defined simply in terms of connectivity in the bulk. It also is defined in terms of an additional component involving entanglement in the boundary. So now, whereas initially we might interpret this as a duality relation, with the quantum correction term added, that seems to be no longer the case. And at this point, I'd like to consider a proposal due to Susskind in an article in 2016, in which he suggests a way to essentially reestablish a duality understanding of the RT formula, supplemented by this quantum correction term. And this proposal is motivated by an earlier conjecture due to Maldacena and Susskind called the ER equals EPR hypothesis, which I'll discuss in a bit more detail in later lectures later this week. Right. At this point, it's the hypothesis that two subsystems of a composite system in an entangled state are connected by a Einstein-Rosen wormhole. So in this 2016 article, Susskind applies this hypothesis to the RT formula with quantum correction. Right. So he suggests, well, this quantum correction term, right, can be interpreted again as the entanglement entropy of a bulk subsystem localized in some region X in the HR part of the bulk with respect to some subsystem localized in some region Y in the HR bar region. It encodes the entanglement of subsystems localized in regions X and Y in the bulk, right? And his proposal then is under the ER equals EPR hypothesis, if the subsystem at X is entangled with the subsystem at Y, then there's a wormhole that connects them in the bulk. And in addition, the measure of the wormhole that corresponds to the measure of entanglement between the two bulk systems, Susskind assumes to be the minimal area cross-section of this wormhole that connects them. And I'll say a little bit more about this proposal of identifying the minimal area cross-section of a wormhole as the measure of a wormhole that kind of corresponds to the measure of entanglement represented by entanglement entropy in my lectures on the ER equals EPR course hypothesis later on this week. But Susskind adopts this proposal, right? And so under his ER equals EPR modified RT formula, we can replace the second quantum correction term, which is a term involving entanglement, with a term involving spatial some feature of space-time geometry, right? In this case, namely the minimal area cross-section of a wormhole in the bulk. So this seems to reestablish a duality relation that we can associate with the RT formula, right? Under the original RT formula, the connectedness entanglement von Ramsdonk's connectedness entanglement hypothesis only suggests that boundary entanglement is necessary but not sufficient for bulk connectedness. Suskind's ER equals EPR modified interpretation of the RT formula reestablishes sort of this biconditional one-to-one relation between bulk connectedness and boundary entanglement. Okay. Any questions at this point? So this is the RT formula with quantum correction term added and one proposal as to how to maintain that it states a duality, an ADS-CFT duality relation. But in order to do so, we have to adopt this other hypothesis, the ER equals EPR hypothesis. All right. So that's the RT formula, and one sense in which it states a duality between quantities on the boundary and quantities in the bulk in ADS-CFT. Now I'd like, in the last part of the lecture, I'd like to step back and consider in general what it takes to establish, what it could take to establish a duality between topology on the one hand and quantum entanglement on the other. And I'd like to approach this question in terms of two approaches, a state-based approach and an observable-based approach. So let's first consider what we might call state-based approaches to a duality relation between topology and quantum entanglement. So the intuition here is that the goal of a state-based approach is to identify topological states that can be thought of as dual to quantum entangled states. As an initial example of such an approach, I'd like to consider what some authors refer to as Ervin's analogy. And this is an example given in an article by Ervin from '97. According to his analogy, topologically entangled inlinks are analogous to quantum entangled in partite states. And then, of course, the relevant question is, can we turn this analogy into a duality relation? His intuition, Ervin's intuition, was the following. Well, in topology, an inlink is an embedding of a disjoint collection of in circles up to continuous deformation, up to ambient isotopy. So as a first example, Ervin asks us to consider this particular three-link, this embedding of three circles known as the Borromean rings three-link, right? So it has the feature that all three circles are intertwined with each other, entangled with each other, in such a way that if you cut any one of these circles, the other two circles become disentangled, right? And Ervin suggests this is analogous to this particular tripartite non-product vector state. Right? This is one form of a GSC tripartite non-product vector state. So the idea here is if we measure one of these three subsystems, so this is a state involving three subsystems in spin states. Right? So if we measure subsystem one, for instance, and get the results spin up, then the other two subsystems become disentangled. Right? The state of our composite system becomes a product state, assuming we adopt the projection postulate. And so, according to Ervin, measurement of a multipartite vector state in quantum mechanics is kind of the analogy of cutting a link in an inlink. Now, to make this analogy maybe a bit more rigorous, to strengthen it, let's recall some definitions from topology. So let's recall that the n-dimensional braid group, B sub n, is the group generated by n generators, little sigma, that satisfy two conditions that are referred to as the, I think they're called the Braden conditions, the Braden relations. And the intended interpretation of these generators is that they act on objects called n-strands, vertical line segments, right? Such that the action of the ith generator, sigma sub I, on the ith strand is to twist it, I guess, counterclockwise about the I+1 strand. Right? And the action of the inverse of the ith generator is to reverse that, to twist the ith strand clockwise about the I+1 strand. So an n braid given by a sequence of generators of the braid group can be thought of as a set of n strands that carries a representation of the braid group. Now, it turns out that every n link can be represented by a closed n braid. I think this is due to a theorem by Alexander. So for instance, we can get the Baromean rings 3-link by taking the closure of this particular 3 braid, right? Identifying the endpoints of the first strand and the endpoints of the second strand and the endpoints of the third strand. And in doing so, we get this closed 3-link. And similarly, the trivial 2-link, consisting of 2 disconnected circles, can be represented by the closure of this 2 braid, right, given by sigma-1 times its inverse. Now, this suggests the following definition. An n-braid can be thought of as topologically entangled just when it contains at least one pairwise set of terms, sigma I, sigma j, that are not equal to the identity. Right. So the 3 braid whose closure produces the Baromean rings 3-link, which is entangled, is topologically entangled according to this definition, whereas the 2 braid that produces the trivial 2-link is not topologically entangled. So this finally allows us to define the concept of a topologically entangled n-braid. Let's let an n-braid be topologically entangled just when it's the closure of a topologically entangled n-braid. Sorry, an n-link is topologically entangled. And it's this definition now that we can compare with the definition of a quantum entangled vector state, right, as a non-product state. So now we can formulate this question. Are topologically entangled n-links the dual of quantum entangled n-partite states? And the answer to this question is, alas, no. And this was demonstrated again in this article by Aravind. So he gives counterexamples to this claim in the following two types. It turns out a topologically entangled n-link can correspond to many distinct quantum entangled n-partite states. So his example is this family of quantum entangled tripartite states. Right, it's a family because you get any particular entangled tripartite state by some particular value of alpha and beta, or by choosing some particular direction for the spin axes. But according to Aravind, this family of entangled states corresponds to just a single, what we call a topologically entangled 3-link. In this case, this is what's called the 3 Hopf rings 3-link. So this has the feature that if we cut one of the circles, the other 2 remain entangled with each other. Right? And that corresponds to, in the entangled state, measuring one of the 3 subsystems. Suppose we measure subsystem 1, and we get the result spin up. The composite state collapses to the first term, right? And that's a term in which the 2 other systems remain entangled. And the other counterexample Aravind discusses or mentions is this one: a quantum entangled n-partite state turns out may not correspond to a definite topologically entangled n-link. Right. So here's a particular example of a tripartite entangled quantum state, and according to Aravind's intuition, it corresponds to either the 3 Hopf rings topologically entangled 3-link, or the Baromean rings topologically entangled 3-link, each with a given probability. Right. So if we measure subsystem 1, there's a probability of a third that the 2 other subsystems become disentangled, right? And that corresponds to the Baromean rings 3-link. If we measure subsystem 1 then there's a probability of 2/3 that we get the result spin up, right? And in that case, the two other subsystems remain entangled. And that seems to correspond to, again, the 3-hop rings, 3-link. So according to Aravind, this single tripartite entangled state corresponds with a probability of 1/3 to the Brownian rings 3-link and a probability of 2/3 to the 3-hop rings 3-link. So there's no simple duality relation between topologically entangled n-links on the one hand and quantum entangled n-partite states on the other. That isn't to say, such a duality can be established in an alternative state-based approach, but it is to suggest that any attempt is potentially problematic. So let me move on now to an alternative approach to attempting to establish a duality between topology and entanglement. And let's call this one an observable-based approach. The intuition here is that the goal is to find suitable dual notions of quantum entanglement observable and topological observable. And an example of this approach is given by a research program that was initiated by Kaufman and Lomonaco in 2002, and a fairly recent review and update of that program is given in this article from 2016 by Alagic and colleagues. So Kaufman and Lomonaco's idea was to focus on unitary representations of the braid group. So a unitary representation of the braid group is a map from generators of the braid group, the little sigmas on the one hand, to n-partite operators that act on an n-partite vector space on the other hand. N-partite operators of a particular form, namely under a unitary representation, the kth generator is mapped to this n-partite operator that is the identity on all degrees of freedom, laticites, if you will, except for the kth and k+1th sites on which it acts like what's called a Yang-Baxter operator. And a Yang-Baxter operator is a bipartite operator that satisfies this particular relation. So the intuition here is that this relation encodes the Braden relations that define the generators of the braid group. So this is sort of the operator theoretic version of the Braden relations. So the idea here is that each n-braid corresponds under a unitary representation to an n-partite operator on some vector space. And then we can ask, then we might define an n-partite operator on a vector space, an n-partite vector space, to be quantum entangling just when there's a product vector in our space such that when we operate on it with our operator O, we get a non-product vector. So now we can formulate the following question. Is a unitary representation of a given n-braid B quantum entangling if and only if the n-braid is topologically entangled? If the answer to this is yes, then this is a way of establishing a duality, right, between topological observables and quantum entanglement observables. But the answer to this question turns out is again no. And Kaufman and Lomonaco demonstrate this by a particular realization of a Yang-Baxter operator. So this is a Yang-Baxter operator defined on 2 copies of two-dimensional complex space. And they show that it's not quantum entangling just when alpha times beta equals delta times gamma, right, where alpha, beta, delta, gamma are the non-zero entries in this matrix representation of it. And this entails that if B is a topologically entangled two-braid, then a unitary representation of it is not quantum entangling for, right, these values of the matrix elements of a matrix representation of the unitary representation. But on the other hand, this shouldn't be all that surprising given Aravin's analysis, right? So we already knew topologically entangled closed braids as topological states are not dual to non-product vector states. So perhaps we just haven't identified the proper types of topological observables. So another potential candidate for a topological observable might be what's called a link invariant, right? This is just a function, that takes values on links that is the same for isotopically equivalent links. Now, to define an appropriate link invariant in terms of a Yang-Baxter operator, it turns out requires this slight extension of a Yang-Baxter operator to what's called an enhanced Yang-Baxter operator. This being a pair where one item is a Yang-Baxter operator and the other object in the pair is some arbitrary map from the vector space V to itself, an endomorphism on V. That has such that R and mu are related in these two ways. So this just guarantees that the Yang-Baxter operator is invariant on another set of operations you can perform on N braids that leave them invariant. I think this set of operations is called the Markov transformations. So given this definition of an enhanced Yang-Baxter operator, we can then define a link invariant roughly as the trace of a unitary representation of an N braid, right? Supplemented by this endomorphism thing. Now we can then modify the last question. We can now ask, is a unitary representation of an N braid quantum entangling if and only if this corresponding link invariant on B is non-trivial? And even this more rigorous attempt to understand duality between topological and quantum entangling observables turns out fails. And this was demonstrated in this review article by Elagic and colleagues in 2016. So they showed that given an enhanced Yang-Baxter operator, it is non-entangling. If it's non-entangling, then the corresponding link invariant is constant and hence trivial on closed N braids. Right. So in other words, quantum entangling of an enhanced Yang-Baxter operator is necessary, but not sufficient for a non-trivial link invariant. So again, our attempt to establish a one-to-one correspondence, a duality relation between quantum entanglement observables and topological observables fails. So maybe we have not identified the appropriate quantum entanglement observables, or maybe we have not yet identified the appropriate topological entanglement observables. So at this point, let me step back and consider a couple of very general questions. In particular, if we think we haven't identified the appropriate quantum entanglement observable, we might at this point step back and ask ourselves exactly what is a quantum entanglement observable that could possibly be dual to a topological observable. And we should be aware that the answer to this question can take one of two forms. So one way to answer this question is in terms of an observable that violates an entropic inequality. So for a bipartite state, density operator state, rho sub AB, an entropic inequality takes this general form S sub alpha rho A less than or equal to S sub alpha rho AB, where S sub alpha of rho is what's called the alpha Rényi entropy associated with density operator rho. Think of it as a kind of a generalization of entanglement entropy. You get von Neumann entropy as the limit, I think, as alpha goes to 1 of the alpha Rényi entropies. And in that limit, you get that inequality between entanglement entropy on the left and von Neumann entropy on the right that appeared in a previous slide. So a quantum entanglement observable might be defined in terms of an observable that violates an entropic inequality of this general form. Alternatively, you might claim a quantum entanglement observable is one that violates a Bell inequality. Right? So for a bipartite state rho AB, with respect to which some two pairs of observables OA, O prime A, OB, O prime B are conditionally statistically independent, then the CH-SH version of a Bell inequality can be shown to take this fairly succinct form. It's the absolute value of the trace of a particular operator, script B, with our bipartite density operator state. And the condition is that that's less than or equal to 2, where the Bell operator is given by this combination of the relevant observables. So the general question is, right, are manifestations of entanglement in the form of entropic inequality violations the same as manifestations of entanglement in the form of violations of a Bell inequality? And in general, I think the answer to that question is no. It's a non-trivial distinction. So there are examples of mixed states in which this distinction becomes non-trivial. So here's an example of a two-dimensional, what's called a two-dimensional Werner state, right? This is a mixed state in which the first term is the projection operator associated with the spin singlet spin a half state, right? And then the second term is just a trivial combination of identity operators, right? And both terms are weighted appropriately by given probabilities. And you can show the following properties that hold for this two-dimensional Werner state. And the first three, I think, are demonstrated in an article by the Horodekis from '96. And the last claim is demonstrated in a thesis by Kramer from 2005. Right, so for P less than a third, rho sub W is non-separable. For P greater than 1 over the square root of 3, it violates the alpha equals 2 entropic inequality. For P greater than 1 over the square root of 2, it violates the CH-SH Bell inequality. And for P greater than this particular value, 0.7476, it violates the alpha equals 1 von Neumann entropic inequality. Right, so this indicates that for a certain range of values of P, the entanglement of this two-dimensional Werner state is detected by an entropic inequality, but not by a Bell inequality. And for another range of values of P, its entanglement is detected by a Bell inequality, but not by the von Neumann entropic inequality, where entanglement is defined in terms of non-separability. All right, so again, that's something to be aware of, right? If we get to the point where we want to identify an appropriate quantum entanglement observable that we want to set dual to a topological observable. And we can ask a similar question about topological observables. What constitutes a topological entanglement observable? And with respect to this question, I think there are three concerns that we need to be aware of. And the first involves non-linearity. So the concern is this: to the extent that quantum entanglement is characterized by an entropic inequality, it cannot be represented by a linear operator. But typical topological observables can be represented by linear operators. So the intuition here is as follows, right? The nonlinearity of quantum entanglement observables is sometimes described in terms of the set of entangled states not being closed under addition, right? Two entangled states, the sum of two entangled states might not be an entangled state. So there's no linear operator that would respond yes when it acts on an entangled state that applies to the complete set of entangled states. And on the other hand, typical examples of what we might identify as topological observables can be represented by linear operators. Wilson loop observables, observables associated with Aharonov-Bohm phases. So that's one concern to be aware of. Another concern involves non-locality, right? So to the extent that quantum entanglement is characterized by a Bell inequality, arguably it is linear, at least insofar as, right, a Bell inequality can be encoded as in the form of an inequality with respect to some linear Bell operator, the expectation value of a linear Bell operator. But it exhibits a non-locality that is distinct from topological non-locality, right? So let's say that an observable is localizable just when it has support at or in a finite contractible neighborhood of a point. Let's say an observable exhibits topological non-locality just when it has support on a non-contractible region of a space or space-time, right? So an example of a toroid, when your space-time or space has the geometry of a torus, right? Observables with support on either of the two non-contractible loops can be thought of as topological, as exhibiting topological non-locality. An observable with support in a contractible region of the surface of the torus or along a contractible loop, on the other hand, satisfies localization. And then we might define quantum entanglement non-locality simply in terms of two observables exhibiting a distant Bell inequality violating correlation. So the intuition here is that topological non-locality by definition violates localization, whereas quantum entanglement non-locality is consistent with localization. Right? Observables can exhibit quantum entanglement non-locality insofar as they can exhibit a quantum entanglement correlation and yet be localizable. So the relevant question here is, are there circumstances in which topological non-locality entails quantum entanglement non-locality? So I'll leave that as an open question. And then the final concern with identifying appropriate topological observables that might be dual to quantum entanglement observables concerns the concept of correlations, right? In particular, can a topological observable enter into a Bell inequality correlation? And in this context, we might distinguish between four types of correlation. And this, the first distinction between 1 and 2 is that distinction that was introduced on a previous slide, right? We might say a local correlation involves only localizable observables, whereas a non-local correlation involves at least one non-localizable, i.e. topologically non-local observable. But in addition to those two types of correlations, we might also distinguish between short-range correlations that go to zero at some sufficiently large separation distance and long-range correlations that do not go to zero. Now, quantum entanglement correlations, namely distant Bell inequality violating correlations, are typically viewed as local and can be either short range or long range. Right? Type 2 correlations, these non-local types, seem to be the types that are relevant to the case of a topologically non-local observable. So the general question then is, can type 2 correlations underwrite a duality between topological and quantum entanglement? In particular, can type 2 correlations, can type 2 correlations be explained by direct causes and or common causes? Right, the intuition here is that the non-locality associated with a quantum entanglement correlation might be interpreted as a correlation that cannot be explained either by a direct cause or a common cause. All right, so to conclude this lecture, right, we've looked at the RT formula as a potential example of a duality between space-time topology and quantum entanglement. And we've seen how, at least in its original formulation, I'm sorry, in its current formulation, in which it contains a quantum correction term on the right, it doesn't quite establish a duality, but there are proposals to reestablish the duality, right? Perhaps in terms of the R equals EPR hypothesis. And then we took a step back and considered, in general, what issues might be associated with establishing a duality between topology and entanglement. And we looked at two types of cases, state-based and observable-based approaches. And we saw that they both have their issues. Okay, I think that wraps up this lecture.